We will now get into the real business of the meltdown attack. Here we will see the first phase of the meltdown attack and how it reads from a memory we choose. Let's say we want to read the data in memory address 100,000. Of course, this address is not mapped into our, is not allowed to be read by the process we are running. And if we run this simple code, byte b equals what is written in address 100,000, we will raise an exception and we will not be able to read this byte b. However, since we are running code in an out of order way, these two instructions that come afterwards may be executed before the exception kills our program. And this is an important thing to remember. So if we write the value of that is written in address 100,000 into the byte b, we may not see it in our application, but it will be written into somewhere in the processor, and we can do operations on this value before the exception is actually raised. There is a raise condition here, but it is most likely that we will be able to run these two commands. Let's try to go over this code and analyze what it does. However, it is important to mention that we need our application, our process alive after the exception is raised in order for us to do the second phase of the attack. And this can be done in many ways, which will not be discussed in this video. Let's just say that we can catch the exception exactly at this phase in a way that it will be raised, but we will catch it and we will be able to do things with our data. Of course, the data will not be written into the value b because the CPU will not allow it and it will raise an exception. But we will be able to do things in the second phase of the meltdown attack. So what we did here is reading the address 100,000 into B, which raises an exception. But the out of order mechanism allows us to take the value of B and do some operations on it. In this case, what we do is we multiply it by 4k. We will later explain in the second phase why we do this. But let's just say we multiplied it by 4k, and then we read into another byte the address of an array we hold at the index of b, which is the value multiplied by 4k. And we can already hint by now that if our array was not in cache, but it was in memory, we only read the page that holds this byte at the index at the value of b multiplied by 4k. Now let's think about it. We do not have the value that we read in a way that we can access, but this data is actually in the CPU in a way that we can read it, and the information is already there. Let us assume that our array contains all possible values that are represented by a byte, meaning 256. And we only read the byte that is the value, that we only read the index, which is the value of the memory we just read. That means that only this value will be in the cache and all other values will not be in the cache. So reading this value will be significantly faster than all the other values that we read. And if we measure the time it takes us to read it, we can know which index was the fastest that we read, and by that know the value. Now let's try to remember that cache does not cache is not ordered by bytes, but it is ordered by pages and cache lines, which we will not go too much into it, but just let us remember that we want to separate it by pages. And so this is the reason we multiplied the value by 4K, assuming our pages are 4K. And so we access the value that we read multiplied by 4K, and we make sure that only this page will go into cache, and only reading this value will be in cache and take us fast time, significantly faster than reading all the other values.